In office hours, I was reviewing many of your solutions, and so what I wanted to do was give you a quick glance of the type of solutions that are presented in class. So your answers to homework should be of the same type of conciseness. So something like this for merge sort. No description of recursing down to the very base case. Very simple description of what merge sort is doing. What Karatsuba did. It's a 4 or 5 line description of the algorithm. What the closest pair algorithm did. That was a little bit more complicated, but again, it fits into roughly 8 lines like this. You can read this and sort of understand what every step is, and more importantly, you can easily see what the running time is. Each of those lines is very easy to characterize what the running time would be. This is the arbitrage, again, 5 lines. This is Strassen, a little bit messier, not written as an algorithm, but still you can see these are the P1 through P7 is what you compute, and then each of the terms of your answers are like that. This is the FFT that we talked about. Pretty simple description. So I want you to focus on writing your homework solutions in this type of concise way. There are many ways to do this correctly, but part of this class is not only finding the correct algorithm, it's learning the technique, and not only learning the technique, but learning how to really concisely and accurately convey that idea to somebody else. As a property of every single one of these algorithms, notice that I describe, this is the problem that I'm solving, the arbitrage problem, this is the input. Very quickly in my solution, within the first 2 or 3 lines, I'm making a recursive call to the same function. All of the problems in the homework will have a similar structure. If you don't see a line like this in the first 2 or 3 lines of your solution, perhaps you're not effectively conveying it, or perhaps you're going down the wrong track. Let's pick up where we left last class, fast Fourier transform. I'm just going to review the first few slides to bring us back to where we are, and then I'm going to continue with the technical discussion of which endpoints we're going to use for the fast Fourier transform. So remember, what does the FFT do? It takes as input polynomial in coefficient form like this. This is a polynomial, and these are the coefficients of that polynomial, a0 through an minus 1. And it outputs the evaluation of that polynomial a at n different points, at particular the n roots of unity, as we found out. And we know from basic algebra that you can go between the coefficient representation of a polynomial and the pointwise representation of the polynomial. Those are equivalent representations. They have the same information. And there was an n squared algorithm that went between the two. The fast Fourier transform is an n log n algorithm that changes between those two. What was the big idea, the divide and conquer idea of the FFT? What we did is we took our polynomial a, written in coefficient form, and we divided it into 2 polynomials. We gathered all of the even coefficient terms, and we gathered all of the odd coefficient terms. And then we used these coefficients to define 2 new polynomials, ae of x and ao of x, each of degree, roughly degree n over 2. Then we realized that we can express a as ae evaluated at x squared plus x times ao evaluated at x squared. So this is the divide step, the divide and conquer step. We divided a into 2 polynomials. This one right here is degree n. ae and a odd are degree n over 2. So we were able to express the polynomial a in terms of 2 polynomials of degree n over 2, just being evaluated at this special point, x squared. That was the algorithmic insight. Then came the algorithm. With that insight, once we knew this equation right here, we could come up with our first version of the algorithm right here. And that is we recursively evaluate the FFT on the even and odd polynomial, and then we recombine them using that equation that we just described. And so these 2 steps are t of n over 2, and this recombination step is order n, because for each of these n values that we're going to produce, we require essentially addition and a multiplication. So the last remaining issue, the technical issue, is which endpoints do we need to pick? Turns out the answer to that question is we need to pick points that have many square roots. In particular, I gave you an example in the class last time using 4 and 9 and 16 and 25. That allowed 1 step of our equation to work. We're going to need this to work for log n steps. The recursion is going to be log n deep. And so we're going to need points that have log n square roots. And there are several candidates. The ones we're going to pick are these roots of unity. the complex roots of unity. There's another choice. You can also use elements of a finite field. So modular arithmetic. Let me not go down that tangent. Let us first identify the roots of unity. So what are the roots of unity? Unity means 1, and the roots mean what are the nth roots of unity. Things that when you raise to the nth power come to 1. Now we had already identified one of them, which is 1, and here are the other ones. In fact, here is a complete set. 1 e to the 2 pi I over n, e to the 2 pi I, 2 over n, etc., all the way up to the e to the 2 pi I times n minus 1 over n. And the reason these are the roots of unity are because of this Euler identity. Okay? If we take any of these points and we raise them to the nth power, then these n's cancel, and you get 1. 1 to the j, or 1. So these are, in fact, n numbers. They're all different, and they're all roots of unity. They're all numbers that if you raise to the nth power, they turned out to be 1. Now that's not the property that I need to show you. The property I need to show you is that if I take any of these things, it will have the right number of square roots. It will have enough of them. Before I can do that, I want to get you comfortable with these numbers. I want to actually show you what they are. What is this number? And in order to get a handle of that, we're not going to go through the Taylor series expansion, although one could. One could expand this around 0 and basically get what I'm coming to. The punchline on that Taylor series expansion is that you can write e to the ix as this expression, cosine x plus I times sine x. And so this gives you a nice formula for e to the 2 pi ij over n. It just turns out to be cosine of 2 pi j over n plus I times sine 2 pi j over n. So as an example, let's compute omega 1 comma 8. That's just going to be cosine 2 pi of 1 over 8 plus I times sine of 2 pi 1 over 8. And so that's going to be cosine of pi over 4 plus I times sine pi over 4, which should be 1 over square root of 2 plus I over square root of 2. Let me do one better. Let me show you for n equal 8 all of the roots of unity. And so this is going to be the first one. It is always going to be 1. We just computed the second one. W2 of 8 is going to be I. W3 of 8 is going to be negative 1 over square root of 2 plus I over square root of 2. And the other roots are going to be these right here. So in particular, if you are to draw the n roots of unity on the complex plane, then they fit around a circle. And this is how you can do computation with them. Now here is the interesting property about the roots of unity that we need for this algorithm. If you take the nth roots of unity and square them, so take each of these numbers and square them, you're going to end up with the n over 2th roots of unity. And I'll illustrate that first by taking all of these 8 points and squaring them. So if we take, for example, 1 here and square it, we end up at 1. If we take this number right here and square it, as we did in class, that's going to be I. If we take I and square it, that's going to be negative 1. Similarly, if we take this number, which is, and we square that, we're going to get negative I. This right here, negative 1, when we square it will be 1. And similar, these 3 points, I'll let you verify. When you square them, you get exactly these points. In fact, there's a simpler argument. I can convince you just by looking at this list right here why this is true, why the roots of unity, the nth roots of unity, when you square them, you get to the nth over 2. So here are the list of nth roots right here. And now let's go ahead and square this set. So let's take 1 and square it. We get 1. If we take this number right here and square it, we get e to the 2 pi I times 2 over n. But another way to write that is exactly as e to the 2 pi I of 1 over n over 2. It's 2 over n. If you just divide the numerator by 2 and the denominator by 2, you get exactly this. So let's do that with this number right here. You'll get e to the 2 pi I of 2 over n over 2. That will continue all the way until you get to this term, n over 2 over n. When you square this one right here, you basically get e to the 2 pi I again, which is 1. This is equal to 1 right there. And you'll see that when you square these things, they also go right back to where they started. So, for example, take e to the 2 pi I n over 2 plus 1. If you square that, you're going to get e to the 2 pi I times n. And if you rewrite that, n over n is just going to be 1, which this is 1 already. And then the remainder is going to be 2 over n, which, as we described before, could be rewritten like that. So all of these elements, when you square them, they just fold right back onto themselves. And as you can sort of see, this 1 over n over 2 is exactly an n over 2th root of unity. So this set of numbers, these roots of unity, have a special property. If you square them, you get the n over 2th roots of unity. That's what lets us recursively apply the same algorithm. So if we start with n over 16, we're going to evaluate a at the 16th roots of unity. And here they are. In the algorithm, we're going to recursively divide this into a, e, and ao. And so we're going to want to, for n is equal to 8, we're going to want to evaluate ae and ao at the n over 2 or 8th roots of unity. When we evaluate ae and ao, we'll also recursively evaluate the even and odd versions of those polynomials, and those will be the 4th roots, and so on until we get the 2nd root, right? And this will be a base case. So that is essentially the algorithm. If we wanted to use our formula, we basically want to evaluate a at an nth root of unity. Then when we square it, we get n over 2th roots of unity. And this right here is a recursive FFT call. It is a smaller version of the same problem. Evaluate a polynomial at the n of degree n over 2 at the n over 2th roots of unity. So where is this going? Our algorithm basically looks like the same before. First step, evaluate AE, the even polynomial, of degree n over 2 on the n over 2th roots of unity. Similarly, do the FFT on AO. Finally, we combine these points to produce A evaluated at all of the nth roots of unity using the equation A of omega I comma n is equal to AE at omega I comma n squared plus omega I comma n times A odd omega I comma n squared. Now, since omega I comma n squared is an n over 2th roots of unity, these points right here will be in these two lists. So we just look them up and use them in this math. Your next homework, homework 3, will have you run the FFT algorithm on a small set of points, on 8 points. And so you'll have to go through this process once just to understand how this algorithm works. It's a really, really important algorithm. I want everyone to know it. What are the applications of the FFT? I'm only going to talk about 2 or 3 of them today, but there are thousands. Remember when we talked about multiplication of numbers? So we took these two numbers and we multiplied them in school book way. Another way of looking at this multiplication is to think of the top number a here as a polynomial. So this is kind of like 1 times x cubed plus 7 times x squared plus 8 times x plus 9. Okay? And similarly, this is 1 times x cubed plus 4 times x squared plus 3x plus 2 for x equal 10. Multiplication of two numbers can be looked at as multiplying a of x times b of x. You compute what the c of x, and then return c of 10. right? So if I wanted to multiply these numbers, I treat them as polynomials, I multiply them, and then I return the evaluation of this c at 10. I'm going to give you an example to make it even more clear. Here are two nice polynomials. One represents the number 21, and one represents the other number 11. Let's evaluate these at a few points. So, for example, at point 1, this right here is going to be 3, and this point right here is going to be 2. And at point 2, this one is going to be 5, and this one is going to be 3. And at point 4, this one is going to be 9. Great. Wonderful. Now take a look at what happens when we multiply these two. 2 times 3 is 6, so we can draw a point right there. 3 times 5 is 15, we can put a point right there. And 5 times 9 is 45, so we can put a point right there. And it turns out that if you draw the polynomial 2x squared plus 3x plus 1, it hits exactly those points. And 231 happens to be 21 times 11. Here is why the FFT is really cool. You can take your number and express it as a so here this was a 2-digit number, but I can obviously take 3 or 10-digit numbers and write it as a polynomial, okay, like I did here. And now I evaluate that polynomial at n points. I used 1, 2, and 4, and I evaluated both polynomials at 1, 2, and 4. And then I multiplied those points. I multiplied these two numbers, these two numbers, and these two numbers.
And then I interpolated the results back into a polynomial and looked at the coefficients, which turned out to be exactly the answer that I needed.
So that gives us a new way to multiply numbers. Let me write it down. What we first do is we write our input as an n-degree poly. Okay, so A and B. And you actually have to pad these numbers with a few extra things. That's just a detail. The next step we do is we apply the FFT in order to get A evaluated at n points. We don't care which points they are. I used 1, 2, and 4 in that example. You could have used any 3 points. I use the FFT to do that. And then I do the same thing on B. I apply the FFT to B and I get B evaluated at all of these points. What's the next step? I multiply these guys together like this. And I got C of omega 0, C of omega 1, etc., all the way up to C of omega 8. So I just multiply. And then the final step was I used the inverse FFT. I didn't describe it in class, but it kind of works like the FFT, where given the point representation, we go back to the coefficient representation. And then, in fact, we're done, because this right here, like 231, I just read off these numbers, and that was my answer. Now let's talk about the running time of this algorithm. This step right here is n log n. This step is n log n. This step, we're going to recursively use this algorithm in order to multiply these guys right here. So there's a trick right there, and this is n log n. Putting aside a few details, this algorithm, it's called the Shonod-Strassen algorithm, and it runs in this time, n log n log log n. And this log log n comes because you recursively use this algorithm in order to perform these multiplications right here. Now remember, previously the best we had done, Karatsuba, had done something like this, n to the log base 2 of 3. There's a few other ways, intermediate, that are slightly better than this, but in 1971, remember this guy, Strassen, we saw one of his algorithms already, the matrix guy. He did that in 1969. In 1971, he discovered this cool algorithm. It was the best multiplication algorithm until just a few years ago. Martin Feurer, he was actually one of the students. I forget whether he was Schonage's student or Strassen's student. He had been working on this problem of multiplication for 20 years. 20 years. And then he had this breakthrough and he figured out how to make all of this stuff work out. By the way, the difference between these two numbers is not significant, but there's so many ideas that were needed to go through there. And so this is really sort of an intellectual tour de force there. Why do we care about this, right? So this is pretty fast, but n log n is very, very fast. So here's a paper that describes how these, in 1971, the people came up with this algorithm. This paper, I think, is from like the 2000s. So it took a long time for someone to actually get through all the details and implement this algorithm, but they actually implemented it, and this is now available in GMP, the GNU Multi-Precision Library. So all of mathematics research that works in very large numbers, they use this particular algorithm. And the final thing I want to say about this, I hope it convinces you that a change of representation is actually sometimes the insight that you need. So if you're stuck with multiplication in schoolbook mode like this, right here, then your life would be limited to some particular path, right? You wouldn't be able to get beyond this type of n-squared approach. The insight to this Schonad-Strassen algorithm is to represent the input as polynomials, and computing the product of polynomials can be done pointwise. You can take these 2 points, multiply them together, and get the points on the product, right? And that is what allows an algorithm that works like this, because here you only need these, in principle, you only need these n multiplications in order to get the coefficients of the product. Okay, so you do n log n to get it in the right mode. You do n operations to get the answer, and then you do another n log n operations to get the answer in the format that you like. Multiplication is one example. There's another practical example, which is convolution. So the example I talked about first, you have this kind of noisy signal, and you'd like to smooth it out by taking, for example, a running average of 5 days. That approach can be written in terms of a convolution. So you have this big long stream of n data items, and you'd like to, for example, take a running average of these 6. So what you'd like to do, if you do this the brute force way, it takes order n times m, right? I do this set of 6 times this set to get one item, and then I shift over and multiply it by this set right here to get the next item, and then I shift over to get the next item. I'm not going to explain it, but using what's called a convolution, which again is polynomial multiplication, you can do this in order n times log m time. Much, much faster. And where does this come into use practically? String matching is an example. So first of all, this convolution is also image filtering. So every time that you take that really glorious Instagram photo with that really hazy blue artsy filter, that is an FFT working in X and Y dimension to apply that filter. More scientific application, string matching. So if you take the DNA sequence, billions, right? Yeah, I would say 4 billion pairs. If we were to sequence your entire DNA, it'd be roughly 4 billion. Genes can be on the order of millions. So if I would like to test your DNA to see if you have a particular anomaly, I need to look in your genome sequence for a particular sequence. I need to find a pattern in your sequence. If I were to do this the silly way, this would basically take 4 billion times 1 million. Okay, so this is like 10 to the 9, and this is 10 to the 6. It would take like 10 to the 15 operations. Using a pattern matching algorithm, we can reduce that to basically times, and so this is on the order of 10 to the 10. Okay, 100,000 times faster using a better algorithm. And moreover, in real DNA sequences, you don't actually want to look for a specific sequence. You have these things called like don't care symbols. I don't care what's there, I just want to look for this particular pattern. This is why FFT is so useful. It finds its applications in all sorts of things, from your Instagram to music to multiplying numbers to doing biological analysis on DNA sequences. I want to finish this unit with another very, very cool algorithm. This is called the median, or ith order statistic. The problem, you're given a list, n elements, and you'd like to find the element of rank n over 2. That is often called the median. Rank means the n over 2th largest or smallest number. You can sort the list and then exactly index that position and get the number. Simple algorithm, you all could implement it because you all know merge sort. Problem is it's n log n. Can we do better? Yes, we can through divide and conquer. In particular, we can abstract it. We can find the element of any rank, rank I, like the 17th oldest person in this class, we could find using this algorithm. And the insight that we're going to use is we don't have to fully sort our list. Sorting is too much work. If we just want to find one particular element in our list, why spend all the time sorting all of that information? That first idea is to use something like a quicksort partition idea in order to help track down the element we care about. You pick a partition element. In some cases, we can always just pick the first element of this list. And what we'd like to do is partition this list about that element. What does that mean? That means we want to start with the list like this, all orange with one partition element, and we want to end with the list that consists of all the elements that are less than our partition element on the left, and all the elements that are greater than our partition element on the right. We start with the yellow pointer here, a blue one, and an orange pointer right there, and a blue pointer right there. And we ask, is this guy less than this element? Let's suppose it is. Then we move the pointer over. Is this guy less than our partition element? Yes, it is. Let's move our pointer over. We keep on moving our pointer over until we come up to this element right here. And let's say this element right here is greater than P. What do? We swap, as I've written right there. We take this blue guy and put him at the last element, and we take the orange guy and move him back over here, like this. And so we continue in this way until eventually the blue and the orange pointer are going to meet in the middle. And now we can basically swap these two elements. There are a few cases, but you can basically swap this partition line. All of these elements right here are going to be less than, and all of these elements will be greater than the partition element. The important idea here is that partitioning with our special moving pointers approach is an order n process. This gives us an idea of how to make a median finding algorithm. And here's what we do. So if I want to select the ith order, we handle the base case if a is less than or equal to 2. Then we partition and P is going to be the index. And now if I, the number that we want, happens to be exactly this partition element, then we return A of P. Else, if I is less than P, then we recursively select on I in the array that's on the left. And otherwise, we select on the right. So we partition our list, and we determine whether I is going to be on the left side or the right side, and then we recursively select on both of those sides, updating our index appropriately. Let's consider the running time of this algorithm. This step takes order n time. This one right here takes order 1. Okay, what about these two lines? Is it going to be 2 times t of n over 2? Is this our running time? This right here would give us n log n, and we can do better. Question in the back, answer in the back. Yes, it's not a 2. There's no 2. If this condition holds, then we do that side. Otherwise, we do that side. We only do 1. And so it's only t of n over 2 plus O of n. And this recurrence, this is going to be order n. The first step was to make this observation that you could partition the list into 2 parts. And if this was roughly n over 2 and this was roughly n over 2, then instead of sorting, you would just recursively partition in the part that you cared about. Now comes the complication. We assumed that our partition is always in 2 equal parts. What happens if we always make bad choices in life? So for example, let's pick this as our partition element, and let's just say that it happens to be that when we partition, we broke it into a list like this. There was one element over here, and everything else was bigger. And then the next recursive call we make, what else could happen? Well, it could be the case that when I use this as a partition element, everything happens to be bigger than that. Life could be such that when I partition using that first element, it turns out that everything is always bigger. Then the recurrence becomes t of n is equal to t of n minus 1 plus O of n. And if you remember from a problem set, We had solved the case when it was Tn minus 5 plus O of n. Let's just say this was a 5. It would be the same sort of thing. Theta of n squared. So if we partition and we're only always cutting off a constant number of elements, we only cut off 1, sometimes 3, sometimes 5, sometimes 1 again. If we're always doing bad partitions, then our algorithm won't work. We need a better idea. We need a good partition element. What's a good partition element? A good partition element is one in which, let's say, 30% of the elements are smaller and 30% are larger. If this is a list of the elements in your array in ranked order, a good partition element is an element in this area right here. Towards the end of this class, when we talk about randomized algorithms, what we're going to argue is that if you randomly pick an element from your array, with a reasonable probability, you're going to find a good partition element. So a randomized algorithm, you could use this simple approach, and it would basically, you could do a randomized analysis, it would work well. But what we're looking for at this point in the course is a deterministic algorithm, one that always works and that can be analyzed to run in good time. Here is the idea. We're going to bootstrap to find a partition element. You'll see what I mean in a second. This, I think, is a really, really elegant idea. Recall, we want to find a good partition element. So the first thing we're going to do is take our list and divide it into groups of elements of 5. And then what we do is in constant time, we compute the medians. We take this 5 right here, and in constant time with a set of comparisons, we can find the medians. And now we put them in this new list. How big is this list? It is this big. Notice we had a little group right here that didn't have exactly 5 elements. We just took the median of that anyway. Okay? So this group is roughly n over 5 ceiling. And now here's the trick. Use select, let's call this list the medians of n over 10 on M to pick P. So this is the first time that we have two functions. We have select and we have partition, and they both recursively call each other. So this is the description, the full description of partition. Divide the list, find the median, gather the medians, and then call select on this sublist. The first step to analyzing this algorithm is to write the recursion for this partition step. So P of n, this takes order n steps. You just group this list. You find the median of each of these lists, again order n steps. And gathering all the medians, this takes order n over 5. And this step right here is what takes the time. S is going to be the time it takes to run select on a list of size n over 5. And so the recurrence for P of n is going to be this right here. Let's remember that list. Why do we want to use this element as a partition? What is so special about this procedure? Let's take each of these lists of 5 elements and let's draw them vertically like this. Let's just put them vertically and let's assume that they're in sorted order so that all of the elements are like this. And furthermore, let's assume that the medians are also in sorted order. So you basically sort all the medians and then sort each of these 5 elements in those lists. All I've done in this slide is rearrange these right here and put them into lists, into columns, and put them in sorted order. First sorted by medians, and then each column sorted by values. In the next slide, all I'm going to do is make that picture a little bit bigger. Oh, by the way, this, let's say, is the winner. It's the one that our partition element actually picks. It's going to have to be one of the elements of this blue list. Let's call it the star. It's the median of the list of medians. I'm going to draw that into a bigger picture. And here's the very cool property about this. Let's take a look at this set right here. Our partitioner, this is P, is larger than all of these elements. The guy we picked to be our partition element, it's larger than all of the ones that I've boxed. Let's count how many elements there are. The total number of blue elements was n over 5, and we took half of them to be smaller, essentially. And now, what I'm going to do is forget about the first column and forget about this last column. This first column might have fewer elements. When our original input didn't have exactly 5 at the end, we could have some stragglers. This could be a straggler. And this last column, okay, it definitely has less than 3 elements right here. But every other column has 3 elements that are smaller than p. This column, these 3 elements are going to be smaller than our star. This column, these 3 elements are going to be smaller than our star. So this right here are the number of elements that are smaller than p. Yeah, the straggler column could be over here at the back, in which case we have a full column over here. That would be great for us, because then we'd have one extra column. This minus 2 is to say, even if there was a straggler, and even not counting my own row, I still have this many rows of elements that are smaller than me. Computing this entire list, that means that roughly 30% of the elements are going to be less than p. One can also do an argument on this fraction right there. Roughly 30% are going to be larger. This gives us the guarantee that we need. This median of medians idea gives us a partition element that has roughly 30% that are smaller and roughly 30% that are larger. It's exactly a good element for partitioning. In particular, the fact that we need is at roughly 7n over 10 elements, there can be at most this many that are larger or this many that are smaller. So that's a picture, right? If this is the result of partition. Partition gave us p, and we know that this side right here is less than 70%, and this blue side is less than 70%. Let's go ahead and finish this algorithm by basically doing the full analysis. So select is going to work as we did before. We handle the base case. We use our special find partition value to find our pivot. Then we partition across that pivot, and then we do this right here. Okay? So to compute the running time of this algorithm, this line right here, remember, was p of n, which we've written right there. So that's going to be s of n over 5 plus O of n. This partition step will take order n. And now these select steps will take 7n over 10 plus 6. So the overall running time of our algorithm is going to be, now this again is kind of a complicated algorithm, complicated recurrence, but your homework had one very similar to it. Now you might wonder, what do you do with things like this and things like this? The final technique that I discussed for recurrences, it was a substitution method. We used it to handle square roots. You also use it to handle things like this. You do a substitution to handle something like 7n over 10 plus 6 into something that's without the plus 6. Then it becomes easier to handle, like our homework problem, and then you can solve the recurrence. If you use a guess and check, you can show that this algorithm, this recurrence converges, solves to theta n. This was the last elegant, complicated divide and conquer.